Final exam review problem number 5. In this one, we're looking at the heating curve of water and trying to figure out how much energy needs to be added to raise the temperature of water from, say, minus 40 degrees C to 130 degrees C. Your numbers will vary on your web assignment. So this is a situation where we have changes in temperature and changes of state, and we need to use specific heat when figuring out how much heat's added during a change in temperature, and latent heat when we figure out how much energy is added during a change in state. So for a heating curve like this, there's several distinct regions. We'll go piece by piece. In part A, this is where we're going from solid at a cold temperature up to the melting temperature of that solid. So we're heating the solid up to its melting temperature. Of course, solid water is usually called ice, and it melts at 0 degrees C. But the same process could occur for all sorts of other types of materials. So we're heating the solid up to the melting temperature, and the heat that must be added is mass times the specific heat of that material, in this case it's ice, times that change in temperature, or MC times 0 degrees minus negative 40 degrees. I won't put in the numbers, you can do that. Now, part B is a phase change. This is the melting phase change. During phase change, temperature stays constant. All of this energy that's getting added is going into changing the internal potential energy of the material. It's breaking bonds, it's reconfiguring the molecular structure of the material. It's not increasing the internal kinetic energy of the material. That only happens after the phase change is complete. So as we continue adding heat in step B, the material melts, and only when it's finished melting does the temperature start to rise. So the heat energy that is added during this phase change is mass times the latent heat of fusion. And you can look that up for ice in this case. Next step, we've now melted all that ice, it's liquid water. As we add heat, the temperature increases. So we use specific heat once again. So we're now heating up this liquid. I'll make this a little more general. Heating up the liquid up to the boiling point. That heat added is MC for the liquid times delta T. Okay, now we're up to 100 degrees C. We're up to the melting temperature, the boiling temperature of water. And now as we continue adding heat, we undergo another phase change, another change of state. That's the vaporization or boiling phase change. And the heat energy required for that is mass of substance times the latent heat of vaporization. And notice that this portion of the curve is the longest. It requires a lot of heat, a lot of energy added to boil all that water. You have to break all those hydrogen bonds that are holding the water molecules together. It requires a lot of energy to do that, so that the molecules get far apart in the vapor state. Okay, last portion of the curve. We're heating up that steam. And once again, we use specific heat to do this calculation. MC delta T, and I guess we're going up to 130 this time. Okay, so to get the total energy, you add all 5 of these together. Now this process is generic. It works for all sorts of materials, not just water. You could do this for iron, for instance. All the numbers involved would be a lot different. The melting and boiling temperatures for iron are different than for water. The specific heats and latent heats are different, but all the formulas are the same. You just need to look up the different values. And again, the main concepts involved here are that during processes A, C, and E, when you're changing the temperature of these materials, most of the energy that you're adding is going to increasing the internal kinetic energy of the molecules that make up the material. The atoms are jiggling around faster. During phase changes, B and C, the energy that's added is going into changing the internal potential energy. It's breaking chemical bonds. Often it's causing the atoms to get farther apart from one another. Their potential energy, generally electrostatic potential energy that you'll learn about in Physics 7, gets increased. And the temperature doesn't change during those phase change processes.